So let's go through some of the steps that would have helped that grower to have a more effective system. And the first one would be filtration. And there are a number of different filtration options here. We've seen some screen filter, coarse screen, cascading filter, vibrating screen, and a rotating paper media filter. So the importance of filtration is to reduce demand, as well as to remove particles that are directly going to clog your irrigation equipment. So putting some investment up front in filtration reduces the chemical cost, and it also increases the likelihood that that chemical is going to be effective against target organisms. And there's this concept of demand here, which is just the difference between what you inject and what you get at the end of the hose. So here, if we, for example, injected 5 parts per million of chlorine, and our pond water had a demand of 3 parts per million of chlorine, we would have a residual of 2 parts per million coming out the end of the drip emitters. And so this demand of 3 parts per million is probably going to vary. So, for example, in the winter where there's less algal growth in that pond, the demand is likely to be lower than in the spring and summer. And so basically what a grower is going to need to do is to continually measure this residual and adjust the injected concentration to account for the varying demand from their irrigation water. If you did not do any of that monitoring, then what could happen would be, for example, in the winter where the demand is lower, you might be putting out, for example, 4 parts per million of chlorine out your sprinklers or drip emitters, causing phytotoxicity on a number of sensitive crops. Conversely, in the summertime, you may not have 2 parts per million residual chlorine left, so if there was any Phytophthora or Pythium in your irrigation water, it would not be effective. And here's an example of some work that we've done here in my lab, where we've taken different amounts of peat in this case, and we've added it into a liter of water. And so we've got 10, 20, 30, 40, and so on milligrams of peat, dried peat from growing media per liter of water, and we've measured the amount of active ingredient from chlorine that's left. So we applied 2 parts per million of chlorine, and we measured the residual chlorine. This was work done in my lab by Gavin Mohammed-Poor, and the difference between the applied concentration and the residual is the demand. So we could say, for example, for peat, that if we have 50 milligrams per liter of peat in the water, we'd have a 1/2 part per million of chlorine demand. So if we had that amount of total suspended solids, where you take all the particles and dry them down, we had 50 parts per million. We wanted 2 parts per million of residual chlorine, we'd need to apply 2.5 parts per million of the injector. And here's another example. This is from a flat floor greenhouse where in the supply tank, before the water goes out onto the concrete flat floor, it had 6 parts per million or milligrams per liter of suspended solids, and picking up some of those peat particles coming back was at 20 parts per million. And sometimes we've seen numbers up to about 200 or even more parts per million of suspended solids coming back from these flat floors. That's a lot of demand of chlorine or some other treatment. One of the things that you can do is you can test for suspended solids. It's a matter of taking samples, taking a water sample and sending it into a water treatment, a water testing laboratory. And I'm sure you're going to have somebody locally who's testing a lot of water for residential supplies, and they could do a suspended solids measurement for you. And in this case, this is before one of these rotating paper filters. And before the water passed through the filter, we had almost 12 parts per million of suspended solids, and we reduced that to about half by going through the paper filter. So this would be the type of test that you could do to check whether the filter is actually removing suspended solids effectively. And we've done some testing in commercial nurseries and greenhouses, and I would just make this comment that many of these filters are not really very effective at the moment, the way that they're configured in terms of removing suspended solids. So there's a lot of different options to choose from on filtration. And really you want to get a professional design. You want to get a water engineer in to give you some suggestions on what filter is going to be most appropriate. Now, what are we trying to achieve after filtration? Well, we want to have, for horticultural irrigation water, we want to have less than 20 parts per million or milligrams per liter of total suspended solids. And if we have any more than that, it's quite likely that we're going to have excess demand for any chemical sanitizer that we apply. So this is the level that's recommended by EPA in the United States. We also want to make sure that our last filter is filtering down to a particle size that is smaller than the openings on any of our emitters, especially if you've got a drip or a mist system. And here are some of the sizes of mesh, which you're probably familiar with, and the diameter. A micron here, 1,000 microns is 1 millimeter. 1 millimeter is about a 25th of an inch. And you can see, for example, that if you are filtering down to about a 100 mesh screen, then that would be 149 microns. Now, we've looked at the particle sizes of stuff, particles that are suspended in irrigation water in a number of different greenhouses, and this is about the median size of most particles that are in irrigation water. If you wanted to filter out to a smaller pore size, you can only go so far with a screen, and you get down to the very small size of actual pathogen spores, and at that point you're needing membrane filtration. And these membrane filters have got pores that are considerably smaller than 1 micron. And I encourage you to see the presentation on filtration from Dram Water, because it goes through some very good guidelines in terms of picking which filters would be most appropriate. Some operations in horticulture have no filters. Others very commonly have only 1 filter, but in reality it's going to be in most applications necessary to have multiple filters in line to get adequate decrease in suspended solids. So that's especially true if you've got surface water, pond recirculated water, or you're using very small emitters. So here's an example of multiple stages. You'd start with a coarse pre-filter, which is a screen that's taking out very large particles. You may have a sand filter or screen filter, which is taking out to a smaller level, and so on, perhaps all the way down to membrane filtration, which is primarily there, not so much for pathogen control or microbial control as it is for removing salts if you've got a high EC or electrical conductivity in your water. So get a professional design that's going to allow you to consistently reduce your suspended solids.